Uh, Hello? Okay, great. Yeah, so thanks for the invitation to speak here. And also I want to thank the previous speaker, so he gave such a nice introduction, so that saved me a lot of work. So today I'm going to tell you some construction of non-abelian self-correcting quantum memory. And so this is based on a few works with my wonderful collaborators. Ryohei Kurabayashi is a postdoc at IAS, and Going Zhu is a researcher in IBM. Okay, so let me just briefly review the why do we need quantum memories? Well, in quantum computers, we need at least two components. So one is the quantum memory, namely we want to store the logical qubits, and we also want logical gates that operate on the logical qubit. So today I'm going to focus on the quantum memory part, but I will also comment about the logical gate a little bit. Okay. So the quantum memory require you to maintaining quantum coherence of your logical state. So, for example, if you have non-self-correcting quantum memories, you will often need multiple rounds of synchrone measurement or active error corrections to correct the errors. And such system is not thermally stable. So once you increase the temperature to be any non-zero temperature, the quantum information will just immediately lost. And the focus of the talk and actually the workshop is self-correcting quantum memories. So in such memory, you do not need to constantly correct the errors. Instead, you just need to cool the system down. And as long as the temperature is not too high, you still have a stable logical state. And there's no need of any classical computer to perform the error correction. So the system is thermally stable. Okay. Now, one of the constant things in quantum computing is trying to encode the logical information as ground state of some many-body gap systems. And the reason we want to encode it we want to use gap systems is because the energy gap can offer some kind of protection. So if you add some small interaction, as long as it's not large enough compared to the gap, then the logical state should be invariant. Now, a large class of many-body gap systems are described by the topological quantum field theory. So in this talk, I'm going to stay in the world of topological quantum field theory. So I'm going to consider liquid topological orders, namely all the excitations can freely fluctuate, can freely move in any directions. Okay, so that would be the system I'm considering in this talk. Okay. Now, this kind of topological orders are characterized by topological excitations. And these topological excitations have an important property that they can be detected remotely. So that means that if you, let's see if I can use this. Okay, where's the pointer? Well, maybe I just point a finger. So it has the property that if you have a topological excitation here, you should be able to tell there's an excitation there by moving another excitation which is very far away from the original excitation, but you're moving in a way such that they break with each other. So any excitations should be able to be detected remotely. So distance can be very far, but nevertheless, there can be a non-trivial braiding phase or braiding matrix if you perform this operation. And this is one of the key principles that describe topological orders. So any excitations in topological orders should be able to detect remotely by braiding. And if you think about this process in space-time picture, so the vertical direction is the time direction, and the horizontal direction is the space direction, then this braiding process can be depicted as a link, as a link between two circles. So one circle describes the trajectory of one excitation, while the other circle describes the trajectory of another excitation. So you can imagine one excitations just stay there, and just stay there. So it's like a straight line in the time direction. Okay.
Sorry,
sure.
Detected remotely?
Right. So it means that suppose there's an excitation there, you should be able to detect this excitation using another excitation which is very far away. And the way you detect the original excitation is by moving this far away excitation around the original excitation. So even if those two excitations are separated very far away, you can still detect it. So that's what I mean by couldn't detect it remotely. And this is a key defining principle for topological orders. It has been proposed by Xiaogang Wen and other people. And this kind of braiding has been very useful in implementing logical operations in fault-tolerant quantum computer. For example, Kitaf. Originally it's used by Kitaf. So he used this kind of braiding process to implement some logical gates. And moreover, if you have non-abelian braiding, namely, suppose you move this excitation far away and around the original excitation, you do not just get a simple phase, but you actually change the quantum state. So you can have some kind of non-abelian braiding. And people have used this non-abelian braiding to get universal gate. The first one, I think, should be Freeman, Larson, and Zhengheng Wang. So this is sort of one important feature of topological order in quantum computing. Okay. Now let me talk about a class of topological orders which are not thermally stable. So while this kind of non-abelian anion braiding are important in universal quantum computing, the anions are particles, and the system with anions are not thermally stable. So this has been shown by many people. So if you start with a topological orders in 2+1 dimension, namely 2 spatial dimension with anions, then as long as you increase the temperature even by a little bit, you'll find that the resulting state can be smoothly connected to the infinite temperature Gibbs state. So there's no topological. So once you raise the temperature, you will immediately lose the quantum coherence. And the reason is that the particles can proliferate. So there are just too many configurations of particles with the same energy. So basically, if you have any topological orders with particles, it's hard to make them self-correcting. So the goal of this work is to find thermally stable topological orders that do not have any particles. So that's the goal. Okay. So for topological orders without particles, all excitations are extended, and namely there are loop excitations or membrane excitations or other higher dimensional excitations. So instead of localized at some point, they are extended. Now there are several challenges for finding such topological orders. Even in the world of topological quantum field theory. The immediate challenge is that such topological orders are actually very rare. So previously, the only known examples are the 40 loop torical and also the 60 loop color code, where the excitations are loops. The basic excitations are loops. And people have shown that this kind of topological orders indeed give you self-correcting quantum memory. But there are just 2 examples, and all of those examples only have a billion excitation. Yeah, go ahead.
Is there not a 4D color code?
Sorry?
Is there not a 4D color code?
You can also do that, but color code is just copy of torical, so yeah.
So is there a difference between the 4D and 60?
Sorry, what did you say?
Why do you specifically say 6D color code? Is there?
Right. It's just because people have studied that. Yeah. You can also consider 60 torical. Yeah, if you like. Yeah.
So why do you say rare? Because any code not dimension 4 has this property, right?
Not really.
Yes, I think so.
You want to avoid particles.
Yes.
Right.
So you just put your qubits, let's say, in the middle dimension, then you will never have particle excitations. And all your excitations will be at least loop-like. Right.
So that's right. But you have to avoid. If you go to high enough dimension, that's the general philosophy. Yeah, just that people haven't really studied them. Yeah.
Okay.
But anyway, you can easily write down example like putting qubits on middle dimensional cells. That's perfectly fine. Okay. My point is that all those examples only have a billion excitations.
Okay.
You don't have any non-abelian excitations in any of the examples. And also periodic examples. Yeah. Right. So another challenge is that we want to study logical gates in those self-correcting quantum memories. So in particular, we want to find a way to construct non-clifford gates that can implement in also quantum computing. So maybe you want to look for some feature such as non-abelian braiding or non-abelian fusion in the self-correcting quantum memory. And also we want to construct systems such that they are sort of plausible to be realized in experiments. So for example, recently people have realized the 4D loop Torrico using the trap ions. And there are also realization for non-abelian topological orders in 2 dimensions. So today we want to construct a self-correcting quantum memory that are similar to the system that I already realized, like similar to the 4D Torrico, and also similar to some of the non-abelian anion systems that are realized in experiments, such as the DA anions. And also, we want to study logical gates in this quantum memory. Okay. So basically, what we discovered is a thermally stable generalization of non-abelian anions. So instead of particles, we discover non-abelian extended excitations. So instead of particles, we discover non-abelian membranes or some higher dimensional excitations. And we also figure out some way to perform logical gates in this non-abelian self-correcting quantum memory, and we argue that it can actually be universal. Okay. So I'm also going to tell you an algorithm in the world of topological quantum field theory for topological orders without particles. So the first statement is that such topological orders can only appear in space-time dimension greater or equal to 5. So in my talk, this capital D is always the space-time dimension. Okay. So the simplest example is the 4D Torrico. And now, in addition, if you require those topological orders to have non-abelian excitations, then the space-time dimension has to be at least 6, namely, yeah, go ahead.
So when you say topological order, you always mean TQFT?
Yeah, I mean, the talk would be staying in the world of topological quantum field theory, yeah. I mean, but you can make similar statements for fluorated fractal model, yeah. So for a certain type of for a certain type of gap system, more general TKFT can still make similar statement, like fluorated fractal model, yeah, in particular. Okay. So this is the plan of the talk. Yeah, also please interrupt me if you have any questions, like if there's any concept that you feel I should explain, please tell me. Okay. So let me give you a few more physics motivation. So one big motivation is what's the phases of matter when you have non-zero temperature, or what are the possible phase transitions when you tune the temperature. So there are several quantities that you can use to quantify the problem. So one is the topological entanglement entropy. The other is the topological entanglement negativity. So the topological entanglement entropy can be computed from reduced density matrix. So you start with a density matrix, and then you just trace out the Hilbert space of some complement region, and then you got a reduced density matrix, and then you compute the von Neumann entropy. Then, as long as the region you focus on has trivial topology, you got a constant part, which is the topological entanglement entropy. And it has been proposed to describe topological correlations, both classically and quantum mechanically. Another quantity is called the topological entanglement entropy. Topological entanglement negativity, and this has been proposed to capture only the quantum coherence of your density matrix. And the way to do that is similarly partition the space into two regions, namely some region A and a component which I call the region B. And then you take the transpose for the states that belong to the Hilbert space of the complement region. So this is called the partial transpose. And then you compute the and you compute the log of the sum of the negative eigenvalues, or the sum of the absolute value for the eigenvalues for this partial transpose density matrix. Then again, as long as this region A has trivial topology, you got a constant part, which is called topological entanglement negativity. Okay. And it has been proposed to capture quantum coherence. So let me just give you one example. So you can compute those quantities in torical in different dimensions. I'm not sure how you can see the. You can just look at the screen. So this picture. Okay. So basically, as you increase the temperature, you will reach in general you will have two transitions. So one transition is when the topological negativity becomes 0, and the other transition is when the topological intangible entropy becomes 0. Okay. So for example, if you start with 2D torical, you'll find our transition temperature will go to 0 as the system size L becomes very, very large, becomes infinite. And if you perform a computation for 3D torical, you'll realize that the first temperature, where the topological intangible negativity becomes 0, actually approaches 0. And namely, even if you increase the temperature above 0 just by a little bit, you immediately lose the quantum coherence. But you still have non-zero topological entanglement entropy, and it only becomes 0 when you increase the temperature to a finite number. So that means that in 3D torical, you have some classical topological coherence, but it's not quantum. And once you go to 4D torical, you immediately discover that you have two non-zero phase transitions. So there's a finite temperature where it still maintains non-zero quantum coherence. And for example, we can ask what's the criticality for those transitions. And in the case of 4D torical, the transitions where you lose the quantum coherence is described by the 4D AC model. So this is pretty standard. Okay. So in the rest of my talk, so I will first tell you what's the no-go theorem for the self-clouding quantum memories in the world of TQFT. And then I'm going to tell you what's the construction of this non-abelian self-clouding quantum memory. And also I will briefly comment on how to study logical gates in those non-abelian self-clouding quantum memory. Is there any question? Okay, so I will just move on. Okay. So the principle I'm using behind the result is this remote detectability that I mentioned in the beginning. Namely, every topological excitations should be detected by another excitations by braiding. And now, if we demand that all excitations are extended, namely they are at least one-dimensional, then it turns out that in order for them to braid, the space has to have sufficiently high dimension. Okay. So if you start with extended excitations with dimension n, and you want to braid with another excitations of dimension n, where n and m are greater than 1. So for this to happen, the space has to have dimension at least n plus n. So from the dimensions of those excitations, and also additional radial direction, where you move the other excitation around, and also the orbital direction. So for them to braid, the space dimension has to be at least n plus 1, which is the radial direction, and 1 for this orbital direction. Okay. And then if you want the excitation to be extended, namely those n and m are greater or equal to 1, then it turns out that space-time dimension has to be at least 5. Or the space dimension has to be at least 4. Okay.
Sorry, yeah. What do you call braiding for like high-dimensional objects? Like if there are two loops, you cannot move them around like through one another, or?
Yeah, that's similar. So you can think about a high-dimensional braiding, taking a planar slice. Okay. So imagine you take a planar slice where this excitation here have some additional is extended in some other n dimensions, okay, but suppressing the picture. Okay. And the excitation there also has some extended, is also extended in some orthogonal n dimension. Okay. And they move around, and their motion can be captured by this picture.
Okay, so for two like dimensional things, this would
right.
really be like have kind of take the slice, right? And then we have like two point light particles, and we kind of weight them around one another, which kind of corresponds to like having the loops kind of go through one another. Is that how I should kind of think about it?
Not really. Well, I mean, so, I mean, for example, if you consider like loop break with each other. So imagine they like flow in one like additional direction. Okay, and this is also flow like some additional direction. Okay. So what you do is that you fix the so this excitation is filling some other direction also, and it has fixed coordinate in other direction, right? So what you do is just to like in this particular like two coordinate plane, you just move one excitation around the other.
Yeah. So let's say it's two loops, right? Yeah. Then what happens? Like you kind of move this one around here, and then.
Not really. So the first thing is that like one of the loop has to extend in, let's say, x direction, but the other loop has to extend in y direction.
Okay. Can you maybe do it with your hands?
I mean, it's like one. Well, you can think of it as like straight line, and the other is like straight line in some other direction. But they have some fixed coordinate in some other direction, and can try to move them around each other.
It has to happen in 4D, right? Like you
I
can't,
see, okay.
can't do it with your hands.
Yeah.
Right. Okay.
Fine. Because otherwise, like the loops will always intersect twice.
Yeah.
Right?
Exactly. Okay. Yeah.
So the way you can see there, so you can try to like bring this excitation like just directly close to. You can try to bring one of them like directly like close the other. So you can ask how many intersections do you get? Okay. So because those excitations extending like orthogonal direction, so that means that you only have one intersection point, and there's just one point in these 2D planes where they intersect. Is there other question? Okay, I hope this is okay. Yeah, I mean, if you have any question, please interrupt me. Okay, so what I talked about previously is the condition for topological orders for topological orders with particles to be consistent. Okay, but now if we further require that there are some excitations obey non-abelian fusion, then there's an additional requirement from the consistency of fusion. Okay. So the rule is the following. So if you have a non-abelian excitation, which is n-dimensional, then there must be also a n-1 dimensional excitation in the theory. So here n has to be greater or equal to 1. Okay. So it can be proved by contradiction. So I'll try to fuse the non-abelian excitations. So let me call it S1, S2, S3, and S4, etc. So if you fuse two non-abelian excitations, you'll get a direct sum of many other excitations, like S3, S4, etc. So if there's no excitations of one dimension lower, then if you start with this fusion rule, and imagine all excitations are very short in one direction. Like if you start with a loop, the loop is very small, so it's almost like a particle. Or if you start with a membrane, and then one direction is very small, so almost like a loop. So if you start with this fusion rule and consider the excitations that are very short in one direction, then this will become the fusion rule of excitations in one dimension lower. But because we assume there's no excitations of one dimension lower, so this kind of like short excitation will just reduce to the trivial excitation. So x1 with one dimension very short will just reduce to 1, and s2 will reduce to 1, s3 will reduce to 1, etc. So now we immediately got a contradiction because we have like 1 on the left-hand side, but we have 2 and more on the right-hand side. So we got a contradiction. So that means that if you have any non-abelian extended excitations, there must be some other excitations of one dimension lower. Is there any question about this argument? Okay. So, and the only exception is when the excitations are particles. So when m equal to 0, so you cannot shrink a particle. So this is the only situation where you can have a non-abelian excitations, but no extra other excitations. So this only happens when the excitations are particles. Okay, and then we can run the principle of remote detectability. Namely, we require there also exists other excitations that break with this non-abelian m-dimensional excitations, and also the extra n-1 dimensional excitation. So that will require that there are excitations of dimension d minus m-3, where this d is the space-time dimension, and also excitation of dimension d minus m-2. And if we demand all those dimensions to be greater or equal to 1, namely we do not want any excitation to be particles, then we immediately conclude that d has to be greater or equal to 6. So that's where the lower bound is coming from. And this is just simple algebra, so we just demand that all of them to be greater or equal to 1, then can immediately get the conclusion. So in the non-abelian self-closing quantum memory, we're proposing the space-time dimension is going to be 6. So that's the minimum dimension, which this kind of topological order is possible. And the non-abelian excitations has dimension 2, and then we have non-abelian membrane excitations. And there are also abelian loop excitations. Is there any question on this point? Okay, so so now let me tell you the construction of the model. So the construction is going to use gauge theory, and as we already know, there are many topological orders that are described by gauge theory, such as torical model or higher dimensional homological code. And let me just flash the corresponding Hamiltonian. So you have the usual x track and z track, where I put a qubit on n-dimensional simplex. So, and there are Pauli operators xz that acts on those qubits in n dimension. Okay. And I'm going to introduce a notation where I'm going to call the Pauli z operator acting on the acting on this Sn. So this Sn means n-dimensional simplex. So the Pauli z operator acting on this simplex can be related to the gauge field living on the simplex. So this is minus 1 to the gauge field. And we can think of the gauge field as an operator value quotient. So it's a map from the simplex, from this n-dimensional simplex to an operator acting on the Hilbert space. So we can think of it as operator value quotient whose eigenvalues are 0 and 1. Okay, so the gauge theory I'm considering is slightly more complicated than just the previous one I showed. So this gauge theory has a non-trivial topological twist. And what it means is that I modify the x track to include some other terms that are not include other terms such as Pauli z or or some control z. So, and one way to think about this model is by dimension reduction. So you can start with a model in one dimension higher, which is described by this simple model. And then you reduce the model on the circle. But you reduce it on a circle with an insertion of operator on the circle. So you want to insert a domain wall when you do the reduction. And this domain wall has an operator which can be described by some cocycle for the gauge field. So and this cocycle has a physical interpretation in terms of topological response of some symmetry productive topological phase. But what you need to know is that as long as you have a cocycle, I can write down a domain wall operator, and then I can reduce the theory on a domain-wide operator to get a twisted gauge theory. Okay, so let me just give you some examples of those co-cycles. So let's consider 2D space, and the gauge field lives on links. So those are one simplex. And one example of co-cycle is as follows. So there's a co-cycle that can be defined on a plane or any two simplex. And the definition is following. So so the co-cycle is can be expressed in terms of the gauge field living on the link. So recall that the gauge field, so this A are the gauge field. So this gauge field are related to the eigenvalue of the Poly-Z operators acting on the links. Okay, so if a gauge field on this link 0, 1 is 1, that means that the Poly-Z equal to -1 on the link. And if the gauge field equal to 0, that means that the Poly-Z equal to +1 on this link. Okay. And the expression of this co-cycle is the following. So it's a product of the gauge field living on the links that surround this plaquette. So for example, if you consider this particular plaquette, then the co-cycle is given by the product of a gauge field that trace along some path, not connect the diagonal vertices, like from 0 to 2. So we can have one path going from 0, 1 to 1, 2, and also 0, 3 to 2, 3. And this operator is only non-zero when both terms in the exponent are 1. So as long as one of them is 0, you got 0. But if both of them are 1, you got 1. So this operator is a control Z operator for like a pair of qubits living on 0, 1, 1, 2, and also 0, 3, and 3, 2. Okay. And more generally, you can define this kind of co-cycles on any triangulated manifold, and using the tool called the cut product. So there's very explicit rule for computing them. And there are also many other. There are also generalization of those cut products, and the generalizations are called cohomology operations. And I'm not going to discuss them. Okay, so let me tell you what's the co-cycle I use in order to get this twisted gauge theory. So this co-cycle is a co-cycle for 3 copies of Z2. So in the simplest scenario, each Z2 lives on plaquette on the space, on the 5D space. And I can denote the gauge field by A and B and C. So recall that those A, B, C are related to the eigenvalue of the Poly-Z operators on the plaquette. Okay. And I'm not going to explain in detail, but just as the co-cycle I told you earlier, you can write down similar co-cycles for those 3 Z2s. And the consequence for those co-cycles is that the ground state is no longer 3 copies of torical, the ground state of 3 copies of torical, but rather there's a selection rule on the correct ground state. So some of the ground state in like 3 copies of torical are no longer ground states in this twisted gauge theory with co-cycle. So more precisely, if you have a state where there's a where the Poly-Z operators for like the first Z2 along this direction equal to -1, then the Poly-Z operator, the product of Poly-Z operators for the other Z2s along like perpendicular direction cannot be also -1. It has to be +1. So you have this kind of selection rules for the correct ground states in this twisted gauge theory. And so, well, let me just quickly comment on this. So you can also use the co-cycle to compute what are the observables in the theory and compute their correlation functions. Maybe let me skip this. Okay. So maybe the more interesting part is that starting with this co-cycle, I can construct a local commuting projective model. So the idea is that start from this co-cycle, I can write down a wave function such that glue the wave function, I will get the correct co-cycle. Okay. So let me just briefly mention. So this kind of construction is very typical if you want to construct the wave function for any symmetry protected topological states, and there's an operator that called the entangler that tells you how to go from the trivial product state to the SPT state, and this entangler can be written explicitly, very concretely, from this co-cycle that I mentioned earlier. Okay. So there's a very standard construction, and then so this is the resulting model. So the resulting model is very similar to the one I showed earlier. So this is not any stabilizer, the standard stabilizer code, but it's a non-Pauli stabilizer code. So the stabilizers are like part of X, and there's also part of CZ, and there's also some flux projector, and another set of stabilizers are part of Z. Okay. So that's the form of a Hamiltonian, and there's a very concrete way to write it down. It might be hard to see on this projector, but maybe you can look at the screen if you're interested. And in the spatial case, when the spatial dimension is 3, and if you take the the qubit to be on edges instead of plaquettes, then this model will reduce to the standard DA non-abelian alliance. So this kind of model is really a generalization of the DA non-abelian alliance. But here, the difference is that instead of particle excitations, we have excitations of higher dimensions. Okay, so let me write down the logical operators in this model. So first of all, there's a standard there's a standard polystring operator given by part of poly-Z operators, and because there are 3 types of Z2, so there are 3 types of such Z-string operator, and they obey a Z2 cube fusion rule. On the other hand, the poly-X string operator itself cannot give you a logical operator, but you have to decorate the poly-X string with additional projector. And the reason is this constraint on the poly-Z string that I talked about. So in this model with non-trivial co-cycle, if you have so if the poly-Z string for the first Z2 equal to -1 in one direction, then the poly-Z string for the other Z2s in the orthogonal direction cannot be -1, it has to be +1. So that means that if you apply a poly-X string, so the poly-X string will create eigenvalue -1 for the poly-Z string in the orthogonal direction. So that means that if you insert a poly-X string, you must project the holonomy. You must project the product of the poly-Z string to be 0 for the other Z2. So that's what this extra projector is doing. And from this formula, you can immediately conclude that if you take the product of this operator, then you will get a sum of the poly-Z string operator. And that tells you that the corresponding excitations will obey non-abelian fusion. So that's one signature that a theory has non-abelian excitations. Sorry? The distance of n to the 2. Right. So, right. I mean, so the smallest dimension, the smallest logical operators are the membrane operators. That's basically where it comes from. Yeah.
Is there a simple criteria for the SPT to give rise to non-abelian alliance application?
I mean, yeah. So if you look at the, it has to do with something called the slam product. So if you have a given co-cycle, you can perform this slam product on the co-cycle, and then use this to construct the fusion rule. and I can see whether it's non-abelian or not. So there's a very concrete criteria for any co-cycle, any group. Yeah. Okay. So as I mentioned earlier, you can also construct this model starting from the usual torical model, like 3 copies of torical model in 1 dimension higher, and then you reduce the model along one direction, but you insert a domain wall, where the domain wall is decorated with this co-cycle. Okay, so now because all excitations are extended, and that means that you can argue that the system is actually self-correcting. So basically, the self-correcting property comes from the competition of the Boltzmann suppression and the entropy effect. So if you have a finite temperature, then excitations with some energy is suppressed by the Boltzmann factor. Not sure how I write it down. Yeah. So like this term here is the Boltzmann suppression for finite temperature, where beta is the inverse temperature. And the energy here for the excitation is related to the size of the excitation. Now there can be many excitation configurations with the same energy. So there is a entropy effect that is counted by the multiplicity here. So let me denote it by a small n. And in general, this multiplicity is a polynomial in the size of the excitation. So that means that as long as the temperature is small enough, then you will get then this factor will be small. And this is the usual argument for the self-correcting quantum memories, such as in 4D torical. Okay, so in this way, can derive the critical temperature. And we also explicitly check that if we couple a system to an environment, so using the polynoise model, and then we compute the decay rate of the logical operator, and we find that indeed, if the temperature is below the critical temperature, then the decay rate will go to 0 as the system size goes to infinity. And this discussion is very similar to other computation for the torical model. Okay, so now let me talk about just briefly mention what are logical gates in the theory. So one way to get logical gates is also using the co-cycle. I'm sorry, is there any question? Is there any question so far? Okay. Right, so let me just double check. Okay. So one way to get logical gate in the model is also using co-cycles. So instead of the previous co-cycles I was talking about, now we can consider a domain wall in the theory that is decorated with some co-cycles of lower dimension. And by choosing different co-cycles, you can get different logical gates. And you can also change the topology of the domain wall. So different topology will also give you different logical gate. And in some situation, you can also consider domain walls with a boundary. Then you can also choose different boundary conditions for the domain wall, and that will also give you different logical gate. So by playing around these 3 different conditions, you can construct like many different logical gates in the model. So for example, if you just focus on the first Z2, then there's a very explicit co-cycle you can write down, and very like various type of submanifold that can give you the logical S gate and logical CZ gate, where those logical operators are very explicit finite depth circuit in the model. So I'm not going to explain that detail, but just that there's very concrete construction to do that. And recently there is a paper that allows us to perform universal quantum computing in DA topological orders. So their discussion applies to the usual DA Anion model using 3 copies of Z2. And the same method can be exactly carried out to this case, where we also construct the model using 3 copies of Z2. Okay, so let me just wrap up. So in our work, we discovered the first non-abelian self-cloning quantum memory, and this can be expressed as like very explicit non-Pauli stabilizers. And we also generalized the construction to infinite many such models in all higher dimensions. And they all have similar topological orders, such as similar fusion, braiding, as the DA onions model. But I should also mention that those non-abelian excitations, I think maybe here. So the excitation correspond to this M operator, non-abelian fusion, also have non-abelian braiding. So using this expression can explicitly check the braiding relation. And they have this kind of blooming ring braiding. So if you have three lists, like you have excitations of like 3 Z2s, it can blend together using this blooming braiding, and you'll find that you got -1. Okay. So, and then we can generalize all those conjunctions to any higher dimension. Okay. And also, we also derived Newton-Logon theorem for like self-correcting quantum memories in the world of topological quantum field theory. In the paper, we also construct a probabilistic local decoder, which is very similar to what we have in 4D torical. So, there are many open questions. So, for example, it would be interesting to explore what are the universality classes at the critical temperature for this model. And also, while we focus on pure state, maybe it will be interesting to explore where there are how to do encoding using mixed state topological orders, which is another very rich subject. Okay, so let me stop here. Thanks for listening.
Thanks for that talk. Other questions? Yes.
So you have this lower bound for when you could have braiding for your excitations. If the excitations are non-abelian or even abelian with phases which are not just 1 and -1, do you also get the corresponding upper bound, right? Because you need to not be able to deform this loop to a point by going through some extra dimension. Sorry. So it seems that if you have non-trivial braiding between something of dimension n and m, then you don't only get the total dimension needs to be greater than n plus m plus 2, but equal to.
Yeah, exactly. Right. Yeah. Just that we are exploring the a landscape of topological orders with extended excitation. So if you have higher dimension, then there can, in principle, there are topological orders with higher dimensional extended excitations that can do the braiding.
Right.
So that's why we only have a lower bound here. If you input more information about your topological orders, then you can derive other results. Yeah.
Right.
And also, let me just briefly comment that this kind of braiding constraint also generalized to fluidity fractal order. If you have excitations that only braid in some particular plane, in some directions, you can also run the same logic.
Right. You just do the same argument in the restricted.
Some restricted plane. Yeah. And also, also comment on this condition from the fusion. So this condition from non-abelian fusion is not just in topological world, but it's very general. So if you start with any non-abelian excitations, you can run in any gap system, you can run the same logic because there's no braiding involved in this argument. Yeah. So this constraint is very general; it applies to any gap basis. So just
one more question, yeah.
And I'm sorry, I think I missed this. Can you say again what was the case in 4 space dimensions? You could make a non-abelian order, but it had no non-abelian excitations?
So if you have 4 space dimensions, then you can only have abelian order. If you demand that order does not have particles, then it can only be abelian. If you want to have non-abelian order, then you have to go to 1 dimension higher. That's the bound.
Did I see one more? Okay, if not, let's thank Po-Shen again. And we're having a 1 hour, 20 minutes lunch break, so you meet again at 2 p.m. for the last talk by Shankar.